The first question is sort of borrowed from Matt Delahanty. Is do you agree that it's better to believe things that are true and not to believe things that are not true? So, do you have an answer for that question? My answer is yes. It's better to believe things that are true. Hello.
Sorry, I had to step away.
Yeah.
I had a
Yeah.
phone call real quick, so I had to step away. I apologize.
All right.
If would you
So I
mind?
wanted
Would
I
you
want to
mind?
kick off very. Sorry.
I'm sorry.
Carry
Would
on.
you mind clicking that hide on your screen so that that little bar is gone?
Oh yeah, sure. There you go.
Thank you.
Okay, so I don't think I'll be able to fill in your answers, but it'd be interesting to know very quickly. So, do you think it's better to believe things that are true or things that are not true?
I believe that it's better to believe things that are true.
Okay, so the next one is kind of a two-part question. Do you agree that truth is best determined by testing of hypotheses and predictions? And hypotheses and predictions do not match real-world observations, and data must be rejected or at least modified. So I would say
Yes.
yes, yes.
Yes, and yes.
Yeah, okay. What shape do you think the Earth is? My answer is almost spherical. And I've given three possibilities, spherical, flat, plane of some sort, or other.
I would go with B.
You go B, a flat plane. Yeah, okay. Do you
Now,
have,
all of that to say for a qualification,
yes,
flat is not a shape. So
um,
I wouldn't
yeah, okay.
attribute a shape to that adjective
It
of flat.
has a flat surface, or are you going with some
Okay, so
strange?
in some of the in some of the silly discussions that go on, some people say, well, what about valleys and mountains? Of course, we're not going to take into consideration
Absolutely.
topography. So my general working principle is when we're discussing flat and level, my basis for discussing that is that the shoreline of any body of water at any scale is always going to be unilateral to the opposing shorelines. Those shorelines are always going to be at the same elevation.
Yeah, but elevation from what? Elevation from a plane or elevation from any surface?
So
Sure.
if we're talking about a body of water, it's going to be where the water touches the land.
Yeah, but so your definition applies equally well to a globe, a spherical shape, as it does to a cube, a dodecahedron, or a flat surface.
Only only if we don't make a distinction because the level and flat on a sphere is from the center of mass. Correct?
Yeah, yeah, but you're so the point is, you know, you said your answer was B, a flat plane of some sort, but then when you gave your definition of that, you gave a definition which applied equally well to a sphere.
Well, only if we don't make a distinction between what I mean by flat and level. So for me, flat and level has to do with the point of reference from my feet at a 90-degree angle. So that is perpendicular to my frame of reference. And that is as far as my frame of reference goes. My being level,
So if you're standing on one shore of a body of water and somebody else is standing on the opposite shore, do you, would you consider that sort of something right angle to you're standing vertically, um, a line drawn at right angles from your feet to a line drawn at right angles from somebody else's feet, that those lines would meet. They'd basically be on the same line. Is that what you're saying?
correct. If we both
Yeah.
shot if we both shot a laser perpendicular to our location, those lasers would be 90 degrees and would never meet. And they would never be obtuse, right?
Yeah. So you're saying that it is a flat level surface,
Okay,
the
sure.
Earth,
Yep.
and not a curved surface. Okay, right. Do you have any model or hypothesis that fits with fits with observations and data?
My working model would be simply the physical Earth itself.
What would that look like?
It looks like what's directly in front of you. So you know that I cut it pretty close this morning. I just couldn't help myself, Miles. I had to
Hmm.
get out and shoot.
Yeah, yeah, and that's
So
great. Yeah.
I got out to the shoreline and I'm looking over the physical reality that I observe. So
Right.
I
So for
don't.
you, sorry to interrupt. Then, so for you, there's no bigger um, model for the Earth. You're only interested, or you only think you've got any kind of model for what you can actually see physically.
So if I were to say win an opportunity to go into a college science course or any scholastic course where they would allow me to present my findings, I would have to create a demonstration that I could bring with me. I couldn't bring the Chesapeake Bay with me, right? So I would have to, at that point, create a a graphic of some sort
Right.
to give an illustration. That's about as
Would
far as
that
my model.
only include the Chesapeake Bay, or would it include, Australia and Japan and the whole of the rest of the
I
world?
think that those would simply be secondary or tertiary since I've never been there. I would only try to present the information that I have and then extrapolate from there to say these observations that I'm making are analogous to where you will be anywhere on the plane. The only thing that we would have to take into consideration would be
Okay.
the different atmospheric elements.
Yeah. Okay. Well, I'm not sure I fully understand exactly what you're meaning, but
Well, let's stay there.
we can move on. We
No,
can
no.
move on, and
Actually,
maybe I'll understand better later.
I
Yeah.
well, no, I actually don't want to move on if that's okay.
Okay.
So I'd
All
rather
right.
have clarity between the two of us.
Yeah.
So how can I clarify things for you?
Well, you've obviously, I would imagine you have been to other places, not just the Chesapeake Bay in your
In
life.
terms of making the observations that I am making, I have been to the West Coast, Ventura County.
Right.
I have made observations over the Pacific, 20 miles to the Channel Island
Okay.
chain. Um,
So the Pacific is there's a continuous coastline from the Pacific round to the east coast of the USA. So you would argue that the water level at the Pacific is exactly the same as the water level on the east coast, and therefore there must be a flat plain, given to some topography, but there must be a flat level plain kind of between
that's correct.
the east and west coast of the
That's correct.
states. So already we're expanding your model up to include the whole of the United States. I mean, does it then continue as a flat plain for the whole of the rest of the world?
Sure. So one of the things that I do in my observations, Miles, is where I station myself, the immediate uh, proximate shoreline for me is a mile away, and I start there and I pan to the right at 180 degrees. I just, it's like
Yeah,
I pan a
yeah,
panoramic view with my
yeah,
video.
yeah.
And one of the things that I've said as I've been panning is I want you to pay attention, audience, that the water that's a mile away from me is touching the shore. That shoreline is level with my feet right here. And as we move down the coast, the only thing that we're changing is distance. And so every single point that we see going into the distance, there is still shoreline there, and that shoreline is always level with the preceding location, including my location. So I'm going to then, as I said before, extrapolate what I see in proximity to me to Virginia, to
Yeah.
Florida, to Scotland, to
Yeah.
Africa, to the Pacific. Sure.
Well, I think, yeah, I think I pretty much understand
Okay.
what you're saying. Although we'll find out whether I do or not later on.
Okay. Sure.
And the last thing on before we bounce on, I want to get on quite quickly because I don't want to. I haven't got a huge amount of time. Do you agree that the source of any relevant evidence or data is pretty much unimportant? All evidence or data should be treated and examined on its own merits, and not say, oh, that source got something wrong before, so they must have got this thing wrong. You examine each piece of evidence, each observation or whatever on its own merits, and
I think that I would be comfortable with that. Yeah.
yeah, yeah,
Yep.
yeah. So that's good. So, what objection do you have to this picture, which is a photograph of the Earth taken from space?
Sure. So the the thing that I've thought about early on when I was going through this information and trying to process it would be if I were, let's say for instance, in 1968, if I were alive and I believed that the Earth was flat, and then you got the Apollo mission, and they produce a photograph of the globe. I would not argue CGI. I would argue that it is not a true representation of our reality because of what I understand about the physics and the mechanics of water. So this image is false because water that is contained, and that is it has a shoreline, so to speak. That water at no point curves in a spherical manner. You know, there's surface tension, there's waves, all of those things. You know what I mean? So if we're talking about, well, I don't say that water is always perfectly glass, right? Because just like the land has topography with troughs and crests, or valleys and mountains, so too water is a dynamic surface. So I'm not arguing for a perfectly glass surface, but I am arguing that from shore to shore, it is always equal in terms of its elevation. So
your objection is that this image and a whole host of others don't fit with what your preconceived kind of idea of what the Earth must be like.
sure. So let's say again, I was alive in 19. Well, I don't even know. Before then, and there was a globe, right? So instead of a picture, we just simply have a globe, which is a model, which is a representation of this picture that you have here. They are representing the same idea.
Yeah.
I would argue with my science teacher that globe is false. That's not real. That's not where we live.
Yeah, but and I can understand that point of view. Someone's produced a model and said this is what the Earth is like based on whatever evidence they've used, and to say, well, that doesn't fit with what I sort of observe around me. The difference here is this is a photograph taken from space of the Earth. So you've either got to argue that when you go into space, something happens to the way that cameras operate, so that this image is what you see, even though this image isn't what is actually down there. Or you've got to accept that this is the shape that the Earth is. You've got to say what other flat earthers say, which is this is a lie. NASA, created this image in some other way.
Sure. Again, I think that I would go back to making the same claim about a school room globe, and I would say that's a lie. So, if someone were to say, well, then are you saying that the people who made this globe are lying? Well, not necessarily. They might just simply be a part of the system. They believe the narrative, so they believe it is a globe. They don't have a problem making the globe. But the people who are ultimately behind the propagation of that narrative, they are lying. If you
The difference here is that these pictures, and there are a lot of them, and all of these, nearly all of these, are actual photographs taken on photographic film with a fairly advanced but standard kind of camera.
Sure.
And even ones from the moon. You can clearly make out Saudi Arabia and part of Africa there. As per maps and so on.
Yeah.
Anyway, I just wanted that that done, and I mean I sort of preempted what you might say, but that's not what you've said. So I'll withdraw that comment that's on screen at the moment, because
let me say this real
that's
quick.
not really what you're saying, is
Sure.
it?
Well, let me say this real quick, if I can get my thoughts back. When if I were to have a discussion with someone on the street and ask them what their best proof for the fact that they believe that we're on a globe, and they said, well, we have pictures from NASA, I would say, okay, I hear you, but how would you?
Well, they're not just from NASA, but yeah, carry on.
That's fine.
Yeah.
Space agencies, whatever. I feel like there is a preemptive strike against empirical evidence when people rely upon these images from space. So
how are these not empirical evidence?
Well, in your previous screen on the slide, right? I cannot take the picture myself, so empirically, I cannot. It's not reproducible. It's not repeatable for me.
Well, that's not true. They are reproducible and they are repeatable
For me.
Right. So that takes me to my next point.
Well, hold on just real quick, Miles. I'm sorry. Okay. I want to try to finish my point on the preemptive strike against empirical evidence. So if I talk to my 14-year-old son and he says, but Dad, okay, so I got to tell you this funny little anecdote, right? So my kids, I'm divorced, and Flat Earth came about right at the end of my marriage, and it was just icing on the cake, the straw that broke the camel's back. My ex-wife was like, yeah, I am absolutely done. But my kids, at least at the beginning, were interested in talking. They're like, Dad, come on, Dad, what about? Mm-hmm. And my son would say, we have pictures from space. Mm-hmm. Now, that is his only proof, right, for him. But I don't believe that is his only proof. And so I would say, okay, Charlie, how would you demonstrate the globe? How would you prove? He has not been schooled in how to measure the geography. He doesn't know how to do that. So that's what I mean by the globe is just simply this nice little hand wave dismissal, slam dunk proof, without having to do the work yourself. Kids today, they don't know how to.
That's fine. That's fine. But I think it's a little disingenuous to disregard all the images of Earth from space on the grounds that you can't take them yourself. And my point here is, do you know what we're looking at on screen at the moment?
I do not.
No. This is a deep sea vent. It's called a black smoker. Okay, and you can see it's got what looks like black smoke coming out, but it's actually thousands of feet under on the ocean floor. And it's a deep sea vent. You can't take that picture. You're as likely to take that picture as you are to go to space and take a picture of the Earth. You need access to special craft in order to get there. You need training and so on. In the same way that you could become an astronaut and go to space and take a picture of the Earth, but you'd have to, Well, maybe, I don't know what age you are, but maybe now you probably couldn't. But when you were younger, you could have done join join NASA, join the astronaut program, and tried to become an astronaut. The same applies to this. Most flat earthers will quite happily accept that that is a black smoker, that these things do exist on the ocean floor, that there are many pictures of them, and that scientists study them, and they have no problem with that. And yet they'll reject the pictures of Earth from space.
So, yeah.
You may have the same objection to this. You may say,
no, I don't actually.
You can't say yes or no what this is.
No, I don't have the same objection. My caveat would be: does this image challenge my understanding of reality?
It might do.
Well, but so far it doesn't. So it's not the same. It's not the same quality of.
There's got to be some alternative explanation, and so how can you find out, what the real answer is, if you like, or whether they are right or wrong? And you do that by doing your own observations here on the Earth, and that's fair enough. I can live with that. I've done pretty much the same thing.
Okay, great.
I got a couple of other silly pictures for you, just very quickly, and then we'll move on to my observations. Have you got any idea what that is?
Mars.
No, actually, that's a scanning electron micrograph of a very tiny micro crack in some steel.
Wow. So you've got some oxidation going?
Yeah. That probably happened during the processing of the sample before the electron micrograph was taken, although I don't know for sure whether it is. Yeah. Do you know what that is?
Something...
It's another scanning electron micrograph of a self-assembling plastic.
Huh.
Amazing, isn't it?
Yeah.
And this?
That maybe some epidermis of some creature?
You're pretty close. It's human tongue.
Ooh!
Again, a scanning electron micrograph.
Yeah. Okay.
Okay. So we can move on to my observations. The point I'm making there is that these, unless you've got access to a scanning electron microscope and the experience and the knowledge and the training and so on to be able to use it, you can't take these pictures yourself. And yet most people will accept these and billions of other pictures.
Correct. And would you mind repeating my my acceptance of these pictures as opposed to the pictures from space? What would be my reason for saying?
Well, these don't challenge your view of what the world is, or
That's
your
correct.
opinion about what the world actually
okay.
is. Yeah. So let's go on to some real observations that I've made, rather than observations that I'm assuming other people have made accurately. Would you agree that on a flat surface, if a camera or the eye is at the same height as an object that's in the field of view, then all other objects in the same field of view that are taller than that object must appear above the object, and things that are smaller will appear below. And to illustrate what I'm talking about, I've got a couple
go back to the previous slide
of examples. Okay.
My initial response is no, I do not agree.
Okay. So let's look at some actual examples. So here we've got some soda cans on a pretty flat floor. You'll see a little red dot on the screen next to the furthest away can. That's a laser pointer that was on the floor near to where the camera was. Just showing that it hits the wall just above the floor surface, and so you can see that the floor surface is pretty level. And where the red line is here is the top of the bottom soda can. These are orange colored cans, mostly orange and blue, and then there's some silver cans above them. And the orange cans, no matter how far they go away, they never appear above that line. They cannot appear above that line, and likewise the base of these silver cans can't appear below the line. Now that's over about 10 meters. This observation is over about 80 meters in an indoor athletics track, and we have some hurdles here, and there's on the far side by the high jump mat, there is a hurdle that's the same size, and to the right of it, a taller hurdle. And you see the hurdles in the near foreground. The camera's positioned exactly the same height as the first hurdle you can see. And as they go further and further into the distance, the gap between each of those hurdles, the first 3 is about 10 meters, I think. And then there's another 50 odd meters to the 40 to 50 meters to the hurdles by the high jump pit, and the cameras are further 10 or more meters further back this way. And all the top of all the hurdles is the same height. They, if your camera's at that height and an object is that height, anything that is also that height must also appear in your field of view at that same height. A taller object will appear above it, and a smaller object, a shorter object, will appear below it.
Yes, except for the one hurdle that's higher than the other ones in the back, right?
Yeah, well, that's a taller hurdle.
Right.
That hurdle is put there to show something taller appearing above.
Yep.
And I've got, if you want another shot, I've got a shot of them all standing side by side so that you can see what the hurdles are like. And
I mean, if you have it ready for the next slide, that's fine.
Yeah, well, I don't actually have them all sitting side by side. So
I don't need it
on this. You're going to have to ask you to trust me.
Oh, sure.
Right?
No worries.
On this particular thing. Now, This is a sort of geometrical fact, and you can draw it sort of side-on view. If you're standing on the left of the screen here, looking over the top of an object, then a taller object in the distance must appear taller. There's no way that it can appear taller. So the top of this green triangle, there's no way that can appear down here if the surface that everything is on is flat and level.
I would disagree.
So how can it appear below? What would you say could cause it to appear?
All right, how about this? How about we take a pause real quick and jump out to the chat? Everyone in the chat, if you're following this discussion, what would be my one-word answer for Miles Davis? Is anyone paying attention? What's my one-word answer? Let's see what happens in the chat.
I haven't got the chat on screen at the moment, so
that's okay. Nobody's answering just yet.
Nobody's answering. Well, give me your one-word answer anyway, because like I say, I want to get on.
Okay. My one-word answer, there it is. Ron Hagberg just put it out there. It is the aether band.
Okay, that's fine. You've I've seen that you've referred to this thing called the aether band. Okay. Do you have any measurement of the height of that aether band above the surface?
I don't believe that it is measurable that way. I believe the only thing that we can measure if we wanted to get into the quantification of it would be to compare it to the objects that we are viewing in the distance, knowing their height and whatnot. But if I'm taking...
Isn't that assuming the aether band?
No, I believe that it's understood, because what I mean by the aether band is simply atmospheric effects.
Yes,
right.
I mean, everybody else calls it refraction of one form or another.
Well, refraction isn't...
Not everybody else, but science. Yeah.
For a point of clarification, for me, in the way that I'm operating my channel and my observations, The ether band is the cause of refraction. They're not
Okay.
equal.
Yeah.
So,
Okay. No, that's fine. I mean, whatever the cause of the refraction is not important. What is seen is refraction, um, and yeah, we can argue about the cause of it. Now, do you have any real world observation where that kind of refraction occurs when you're some distance above the surface? In my particular example, oh, this is just showing what happens if you
lower
have
and
the
raise. Mm-hmm.
camera lower than the height of the object in front,
Yeah,
then a distant object can appear below, and if you have the camera above, then in fact even objects of the same height appear above the line.
sure.
That was
Yep,
just to finish that off.
yep.
Um, you may have seen this particular picture already. I don't know if you have. But this is taken from an elevation of 221 meters up on top of a hill. And so we're not looking over water. There is a river estuary in between us and the distant mountains, but it occupies only a couple of kilometers at the most of that distance. And the furthest away mountain you can see there is 137 kilometers away. So we're basically looking over land and not over water here. This monument on the left-hand side of the screen is 210 meters above sea level. So the camera is looking slightly downwards towards the top of that monument. And if we place a line across the screen, following what we saw from the hurdles, then anything that is 210 meters or shorter should appear below that line, and anything that is taller than 210 meters should appear above the line if the surface of the Earth is flat.
If we're dealing with only straight orthographic geometry, sure.
Yeah, and to date, there is no one's been able to show me anything that people can draw pictures on a piece of paper and say this is what you're looking at. The problem is that what they draw is completely unrelated to reality, so they can't give a reality example of the same thing. So these mountains are 974 meters, 927 meters, and 1,011 meters above sea level. And the distances from the camera are given. They're over 100 kilometers. Now, if you actually look at what a flat Earth model predicts you should see, that's shown on the left-hand side here. We should see the top of the tower is the red and yellow object in the foreground here, and the mountains are given by the sort of crude mountain cartoon. And we should be seeing the majority of that mountain up above the height of the line, up above the height of the object. And the same with all three mountains. The globe Earth model, based on the 6,371 kilometer radius spherical Earth, as we saw in the photographs of Earth from space, says that the top of the tower should be almost level with the top of Ben Lomond here. It should be well above the top of Ben Narnain, which is here, and should be above the Benim peak here. So what we have is a perfect match between the real life observation and the globe Earth model predictions. And you agreed earlier that one of the best ways to get to the truth about anything and about reality is to make predictions on the basis of hypotheses and then see whether they are borne out in reality. And so this is, I think, a really good example of the globe Earth model making a prediction that is borne out in reality.
The points of disagreement that I would make, first of all, I wouldn't make a prediction. Second of all, the globe Earth model represents more accurately the concept of perspective. And third,
The perspective is taken into account in both these model predictions. They both have perspective factored into them. The change in angular size as an object gets further away from the observer, or the change in angular size.
Okay, so what I'm understanding you to, in the flat Earth model diagram beneath the picture, those distant mountain peaks are Ben Lomond, Ben Narnain, and the other one.
Yeah.
So you're showing the y-axis into the distance. Okay, so the other qualification and elaboration on the fact that when I say I wouldn't make a flat Earth model prediction is that the reason why I will not make predictions is because, or rather, let me say it this way. The reason why I won't make a prediction about what I expect to see is because the ether band will simply laugh in my face and do whatever the hell it wants. I cannot predict what the refractive index will do to the image.
Well, I think actually you can, if you know what the refractive index is.
I know.
There's some very good physics on this, and it's been studied for a long time. I'm not an expert on optics or refraction. As I said, I'm a biologist by training.
Yeah.
But I think that's not true. My other point here is because we are at a good elevation. I've got a little example to show you. Actually, I'll bounce onto that. I'll just scoot past these bits because we've already seen that. That just shows the line coming in and showing that it matches the model. This is another observation on another day of the same area. So now I'm actually on top of that tower, taking a picture. So that tower is one that you can climb up.
So the one in the previous image? In
the previous image. So this tower here on the left-hand side, the Hopeton Monument, there's a spiral staircase up here and a viewing platform here where you can take pictures. And the central tower here, so this is the river estuary that we're now looking out over, which you couldn't see before because it was behind these low hills. So the river estuary is in back here.
Okay.
So this is taken at far less zoom because I needed to get the bridge in on the left-hand side. There are actually 3 bridges here.
Yep.
And the central tower of this bridge is 210 meters above sea level. And so I'm at 210 meters above sea level on the Hopeton Monument, and this is at 210. So I'm looking exactly straight level across. And the same 3 peaks are on the right-hand side here, as well as a bunch of other ones, all at different distances from the camera. So Meikle Bin, for example, and Earlsea appear slightly above the line, but they're quite a bit closer to the camera than some of the other peaks, and some of the other peaks are lower. So if we pop along here, so we get to Ben Lomond again, Ben Narnain, and Ben Eam. And a little bit hidden by, onto another picture, a little bit hidden by cloud here, but you can see the top of Ben Narnain, and the image is much the same. There's no way that those should be below the line if we're looking over a flat plane. But as I said before, if we're on the globe and the globe matches the accepted scientific model that we have at the moment, then this works out exactly. And I've actually used most of these numbers, and I haven't got that to present today, but used most of these numbers to make a calculation of the Earth's radius on the basis of them. And there are a few of them come out very, very close to the accepted Earth radius. The rest are close, but not quite so close. But obviously, these are pretty crude kind of measurements that I'm able to make of where I am, the distance I am, and how high above or below the red dotted line the peaks actually appear. So I have to estimate that, and everything comes out at around about between 6,500 kilometer radius to about 7,000 kilometer radius, or thereabouts, which is pretty accurate, I think.
Okay. Would you mind stay there, please? Would you mind going back and restating your claim that there is no way about the observation in the red line? Can you restate that comment?
So I think it might be okay. So here the upper silver cans never drop below the eye level or the camera level, and the lower orange cans can never rise above that level.
Yeah.
And the original one was stated here. Hopefully I stated that right, because I wrote it out pretty quickly.
No, I understand that. Yeah. If we could still just go back to your distant observation of the entire the bridges all the way to the other three mountain peaks, and then again, just simply please restate.
You want the bridges picture? Yeah.
Right there. Right. So after you gave us all of the arrows and the identifications, you said there is no way that these should be below the line. Is that what you said?
Yeah, the peak of these mountains, particularly the three mountains on the right-hand side, there's no way they should be below that line if the Earth is flat.
Okay.
If the Earth is spherical, it makes perfect sense. But if the Earth is flat, there either has to be some sort of really bizarre, outrageous refraction going on. We're talking about Benim is, if we go to this picture, Benim is 1,011 meters above sea level at the peak. That peak is some considerable distance below the line. So we're talking more than 800 meters worth of refraction. And one of the reasons that I went to this location and made these observations is I wanted to get up above this area close to the surface of the Earth, looking over water where there are lots of refraction effects going on.
Now that
I wanted to get something that far in the distance that should have dipped down well below. So effectively, our red line here is like if sea level rose by 210 meters, that would be sea level. How can mountains that are 1,000 meters above sea level now disappear below a 200-meter sea level rise? That's another way of thinking of it.
Well, yeah, but I don't really want to go down that trail because that's not reality. We don't have sea level doing that in this image. But I do.
We do. That's the point. Yeah, you can, if you raised sea level by 200 meters everywhere, okay, over the whole surface of the Earth, Ben Lomond, Ben Narnain, and Benim would poke up above that 200-meter sea level, sort of position. They would be up there, and if you stood on top of, with your feet wet, on top of Traprain Law, where I am taking this picture, you would be able to see them on a clear day.
Okay, so
but you can't. According to this picture, they're below sea level if sea level rose that much.
Okay, so let's see. From your observation position right now, how far away are you from the monument?
The monument is 8.2 kilometers. The figures are on the screen.
From you. Okay, I see.
Yeah,
Okay.
that's the distance. So it's first the height of the object and or the feature, and then the distance from the camera.
So when you go
So
to
it's
the
8.2 kilometers, 125, 135, and 137.
okay, so when you go to the next frame and you are on the monument,
Yep.
those mountains on the far right have simply changed their distance from
Yeah.
you.
So
Hold on
if
real
I
quick.
put
Hold on. I'm
if
sorry.
I put the
Just real quick.
figures in,
Let me make my statement real quick, please.
yeah.
Because you have moved yourself 8.2 meter or kilometers, then those mountains
The
are
angles changed as well, so the distances are different.
sure.
You're not just 8.2 kilometers closer, but I've put all the distances on screen for you to see again.
Yeah, yeah. I understand conceptually what I want to address, but I want to still go back and have you you kind of restated the thing about there's no way that these mountain peaks should be below this line, and my only response would be, again, that the ether band is the variable that is causing this dissonance for you. As you look out and you think, why isn't this happening the way I think it should? It's the ether band. So you said there should be some crazy refraction going on. That's
Well,
correct.
it would have to be over that distance,
That's correct.
800 meters. But the point is, over shorter distances, it would have to be considerably less. So
That's correct. So if we go back
if you
to
look
the
at Kernoch Hill here, this is 413 meters above sea level at the top, and the arrow points to where the peak is, and that's falling just below the line. And the line is our 210 meter above sea level line. So a couple hundred meters of Kernoch Hill is of this sort of refraction effect is occurring when we look at Kernoch Hill.
That's correct.
And then 800 or 1,000 meters when you look over at Benin.
That's correct, because now you've got the difference between the Kernoch Hill and the Namin is something like 47 kilometers.
Yeah, it's about it's about
Right.
50 kilometers.
Correct.
It's about 50
So
kilometers, but Kernoch Hill is it's 80 kilometers away. And it's got a less of a refractive effect.
I understand that. I understand that perfectly. So you also have more clarity with Kernoch Hill, right, because of its proximity to you, and the Bien Namin is got more obscurity because of the increased distance. So you have the ether band in this image at 180 degrees in front of you. The difference is that you, on the left, you have proximate observations, and on the right you have distant observations, and that is the variable.
I'm sorry, but Kernoch Hill is 81 kilometers away. It's hardly close by.
What I mean by proximate is in terms of comparing.
And the bridge there is 40 something kilometers away.
I don't want to split hairs on proximate and distance. I'm referring to your images in the distance. Everything is in the distance from you. However, the first peak that you have, I don't know how to pronounce that. How would you pronounce that?
Which one? Mikul Bin.
Mikul Bin.
The one on the left.
Right?
Yeah.
Mikul Bin is distant from you, but it is also more proximate to you than Bien Namin.
Yeah.
Okay. So the difference between your hurdles and your soda cans is distance and atmosphere. If you had more distance, that would change the way that those things would behave in your field of view.
And so your argument is that the ether band distorts the image by exactly the amount of to mimic exactly the amount of drop that we would expect on a spherical Earth.
Well, that would be your burden to prove that there is an exact drop. I'm saying, and this is where I have an outstanding relationship with Barney Tierspell, I think. Barney Tierspell.
Yeah.
I,
I like
I like Barney very much. And so he has volunteered to crunch the numbers and give me the mathematical representations of what drops should be. And my outstanding claim is that the ether band is going to say, I could give a shit what your measurements are. I'm going to do my magic. And so the ether band, yes, is a dynamic element that I do not believe can be quantified.
Okay, that's fine, but I showed you what the globe Earth model prediction is, and that's these are the numbers crunched for this observation on the right hand side of the bottom of the screen.
The problem,
and they mimic very, very well what is actually observed.
the problem,
This observation has been repeated on different days, different weather conditions, and always looks very, very similar. Yes, very small changes, but really, I'm talking about, there'd be a pixel or two higher or lower in the image here, not nothing more than that.
the problem is, and this is where I think my challenge and my statement that's outstanding before Barney produces his results is, I have an image that I have 5 images that I provided for him. And those images aren't going to change. Those images are going to show you what I captured from my location and my height and my distance and the temperatures of that day.
Yeah.
So the thing that I find the burden that you would have to prove is that there is that the atmospheric effects that are having an effect on these mountains equal the mathematical formulations, and that is where I do not believe
that's your responsibility to establish that, right?
Well, no, that's not my claim.
I'm saying the globe Earth predicts that we should observe what is in the bottom right corner of the screen here. I've made the observation and it matches the globe Earth prediction.
Okay.
At that point, I have done made my observation and it tallies with the hypothesis, if you like, or the globe Earth model. Okay. I have here evidence that supports that globe Earth model. Now, what you're doing is you're claiming that there is this thing called the ether band, which will distort distant objects such that they appear the way that we see them here, even though on a flat surface with no atmospheric effects, we would expect to see something entirely different. So it is your job to A, explain exactly how that works, and B, to demonstrate that it is what is occurring. It's not my job to do that. I have produced evidence that matches perfectly with the globe Earth, and at the moment, all I hear from you is, not wanting to be rude, but it's woo. It's there's some magical thing going on that distorts everything so it appears just like it would if it was a globe. And that's pretty much what you said about the pictures of Earth from space. You didn't say they were CGI, you didn't say they were faked, you just said then they in some way, somehow, the camera takes a picture that looks like the Earth is a sphere when it isn't.
So let me try to collect I know. I've heard you say it. I've heard you say that. I know. I've heard you say that. Let me try to collect the thoughts that I have to respond to your previous words. the way that I envision this is, let's say for instance, before you went out to take these observations, you knew where you were going to go, and you knew the mountains that you were going to try to capture. So you
Actually, I didn't.
okay,
Um,
well, just
when
like
I
you,
when I
hold on,
went,
Miles, please, hold
can I
on.
finish? Can I explain quickly? When
Sure,
I
go
first
ahead.
went to this location, um, from the same place where I took this picture, I was actually taking an image across past the bridge here towards the hills in the distance. And it was those hills that I thought I would be able to see, not the ones on the right-hand side of the image here. It wasn't until I was studying my videos later that I realized I'd actually got something even better by finding these three mountains. So they weren't even in my mind when I set out.
Okay, regardless of whether or not you took the picture prior to crunching the numbers or crunching the numbers prior to taking the picture, my point that I was going to try to make is that, let's say for instance you took the picture, then you know you knew your location, you knew the distances, all of that. You went back and crunched the numbers, and then you looked at the picture and said, "Yep, that's exactly what the math says." Okay, I don't believe you can demonstrate that or prove that in the picture alone, and here's the reason why. The reason why I'm going to respond the way I am is because in my observations on different days in manifold conditions, the same objects do not present themselves to me at the same height or the same depth. And so what my request would be for you would be to go back to this location over a year, as I have done, and show me that this never changes. This view that we're looking at right now, if this view never changes, then I'll take your argument seriously.
I've been there 4 times over a 6-month period
You,
so far, and I've actually been there about 10 times over that time, but often the weather is not
I
sufficiently
know.
clear
Yep,
to be
yep,
able to see what I want.
yep, yep.
But I'm
I
sure you've
totally
been there with
understand
your
that.
own observations as well. It's
Sure,
yeah.
sure,
But
but
so I accept that it needs to be to be absolutely certain of this, you do need to try to eliminate strange atmospheric effects and so on, and repeating the observation many times will help. I've invited numerous flat earthers to go there with me, and no one has yet accepted that
well, I
invitation.
would love to do that because I would love to visit Scotland.
And several of them actually live quite close by, and they have decided to completely ignore me on the grounds that every time they encounter me on the internet, I ask them when they're coming to Traprain Law with me. However, this is not the only observation. It's probably the best and in many ways the easiest to understand. I actually made, I think, 9 or 10 separate observations from the same area, all of which support the globe Earth. And those are detailed on my channel. I'd like to quickly look at one more, if that's okay.
Yeah, yeah, no worries. Go ahead.
This is a picture looking in the opposite direction. So,
Can I stop you just real quick?
yep.
This is a tongue-in-cheek comment for everybody out there. Eyes to see Danielle. Would you please start a GoFundMe for me so that I can go out to Scotland and meet up with Miles Davis? Thank you.
Yeah. So this is looking. This is a zoomed-in picture, but it's looking in the opposite direction, out over. So I'm fairly close to Edinburgh, where these pictures were taken, just to the east of Edinburgh, and we're now looking out into the North Sea, across the estuary into the North Sea, and this is an island called the Isle of May. Now, the distance is nearly 26 kilometers from the camera, and the camera was a little bit lower on the hill for this particular observation at 210 meters, not 221 as before. The focal height of that lighthouse, so that's the point where the lamp actually is, just above the horizon here, just below that sort of little black triangle, which is the top of the lighthouse lightroom roof. That's 73 meters. So we're looking down towards the top of the lighthouse, at that point there. Now, if you put these into a curvature calculator, if the Earth was flat, we would expect to see the horizon well above the top of the lighthouse. The lighthouse top would be where the top of the mountain is here. What we actually observe is that the top of the lighthouse is above the horizon, which is in pretty good agreement with the globe model. And I actually drew these out in orthographic view to scale, and obviously it's the triangles are very, very small, representing. I should be able to zoom in on this a bit. So you can see here's where the camera is. The little triangle here would be the top of the lighthouse, would be the very top of that triangle. And if we're looking straight across the top of the lighthouse, we should see a point. The water should appear directly in front of us if the Earth was flat, sort of at 39 kilometers away is the bit of water that should be exactly level with the top of that lighthouse. And that water should continue to rise up in our field of view way out into the distance.
Okay, so can we go back just real quick? Okay,
okay.
Hold on, just real quick. You have it there on the bottom one, but what I was gonna ask you. Can you go back up to the topper, the higher image? Is there any way you can eliminate the line that is not parallel?
Not at. Well, they're not parallel. I can't in this full screen presentation do it.
Okay.
I have to go out.
Okay. So then I have a question.
If you're looking above, if you're looking along above the quite well above, almost twice the height of that island and the lighthouse, then you should still be your line of sight will still hit the water. On this occasion at 65 kilometers. We should certainly see plenty of water if the Earth was flat. On a globe, if this is modeled to scale, taking a line from the top of where the camera is at 210 meters equivalent, looking straight over the top of that lighthouse there, the line of sight never touches. So the horizon, I think from that height is at about 51 kilometers, but our line of sight never touches. It's always above and continues to go on and on and on and never makes contact with the globe, which is exactly what we actually observed. How do I get out of this thing? Like that. Okay, exactly what we observed in the image here. We're looking out, and the horizon is below the top of the lighthouse. So our line of sight above the lighthouse
what I would say is that the horizon is actually in line perfectly with the lighthouse. The thing that you are looking at is refraction and mirage, and that is obscuring the water from extending into the distance.
Right, that's interesting. Again, I don't have it in this particular presentation, but over to the left-hand side, a little bit further round, so not in this particular frame view, I could see land that was over 94 kilometers away.
Without seeing the image, it would be difficult to discuss it.
It was. I'm waiting for a day where I can get a better a better view of this. But you can see land is 94 kilometers away. And other people have made the same observation. Now, the point I'd like to make is that this observation here matches the globe Earth prediction. Again, it always appears the same. I mean, given tide height changes and so on having some small effect, and atmospheric conditions having some small effect, is always essentially the same, with no difference. You never see what the flat Earth model predicts, which is the horizon way up above the top of the island.
Sure, and that's going to go back into Miles, my qualification that you will never hear me make a prediction. Can you go back to that previous image, please?
Yeah, the model one.
This one,
yeah.
yes, thank you. Excuse me. So let me try to get my thoughts back. So I will never make a prediction as to what I will see. I'm going to bring my mouse. I'm not sharing my screen, so let me do that real quick, and then you can see my mouse while I do this little explanation. All right, so here's my mouse.
I can't see anything.
Maybe
I'm on a full screen version.
Maybe you need to stop.
I understand that you're.
Well, let me make my claim.
Having effect, and so this prediction does not match anything that you might expect, shall we say, on a flat Earth, and that's fine.
Hold on, Miles. I wasn't able to make my point.
Yeah.
I know that you can't see my mouse. I don't know if that means that you need to stop sharing so that you can see my sharing. Maybe try to stop sharing.
I might need to do that. I'm not.
Although if you stop sharing, then the image is going to go away. Yeah, we're screwed. So
yeah.
Yeah. Okay. Go back to sharing again and pull up that image, and I'll just talk through it. You can see the image that you're looking at, and I'll just talk through it real quick.
I think I understand what you're going to say.
Let's not do that. Let's not do that.
I'm happy to accept it.
Yeah.
Here we go.
Okay. So the only prediction, Miles, you will ever hear me make is that the ether band is going to kick us in the ass when we try to make declarations about observations, so that all of those lines that you have above that that flat Earth image on the left, I'm going to tell you that my prediction is that the ether band will obscure that and make the water level appear at whatever level it wants to, so that the horizon is not a fixed geographical location. It's only and always and ever will be apparent.
Okay, but in order for that to match reality, okay, the ether band has to have an effect that entirely matches what we would expect to see on a globe of 6,371 kilometers radius.
And that is, again,
because that's what we actually see. What the actual observations match that model.
Right, and I'm sure that you've heard what's the word I'm looking for? The rhetoric. I'm sure that you've heard the rhetoric that the globe Earth calculations is simply hijacking perspective.
Yeah, but that is a nonsense.
It's not.
And B, shows that whoever's saying it doesn't understand perspective. And I've heard people make these sorts of claims. I've shown at least one flat earther, and probably more than one, that those calculators take perspective into account.
But they don't. They do not.
They absolutely do. And what is more, what those calculators, especially Walters, which is fantastic. What it does is it mimics, pretty much exactly. I mean, hesitate to go to the Lake Pontchartrain observations, but Soundley's observations of Lake Pontchartrain match exactly what the globe
Except there's a glaring
predicts.
elephant in the room with the still capture that I've seen for Pontchartrain, and I'm not sure that I can pull it up in this short amount of time. And that is, if you go back to look at that still image of Pontchartrain where you have alleged curvature, there is a distant tower that is twice as high,
which matches perfectly what should be seen.
Well, that hasn't been addressed, so
it's... Yes, it has. Yes, it has.
Oh, really?
And it...
Do you know where I can look that up?
I've spent a long time defending Soundley's observations.
Do you know where I can look up that being addressed?
So I mean, I haven't got that to hand, but I mean, I can.
We're on Skype, but I would love to see anybody interacting with that distant tower. The thing that I'm going to wrap up with, because we are at 10:30, we are at an hour and a half, is that again, I would be more satisfied with your presentation if you had numerous observations to present to show that the images do not change in their appearance.
Well, the two pictures you have seen were taken on different days, about a month and a half apart. But the problem, and I have made the same observation on several occasions, and a whole bunch of others, including some over water, like the one that's on screen at the moment.
Hold on, just real quick, Miles. So, even though you made the qualification that the two images that you showed earlier were taken on different days, those are two different locations as well, so they're not comparable.
Oh. So it's interesting the way the goalposts move.
That's not moving the goalposts. We're discussing two different locations.
Other people say, "Oh,
don't bring in what other people say, Miles. You're having a discussion with me, Miles.
One place, you have to take it from multiple places."
No. Okay, listen, Miles. You are straw manning me right now. You're straw manning me right now because I haven't made those claims. You're having a discussion with me, and if you want to go back and listen to this video again, you will clearly hear the claims I'm making. I'm not asking you to change locations.
I'm not saying you did say that, and if you play,
but it's irrelevant to bring those points up.
You'll hear that I did not strawman you. I told you what other people had said.
But those don't belong in this discussion, Miles. They don't belong.
No, I simply offer it as an explanation for why I selected those two particular views. I told you that I've been there and I have made that observation on 4 separate occasions from the same place, and I've made it on a couple more occasions from the second location over a period of about 6 months, and it never changes. Similarly, the observation that's on screen at the moment from of 4 islands in the 4th estuary. This is taken from a different place called Kinghorn.
Let me just stop you real quick, and then we can wrap up with this. Let me stop you real quick and go back to your last statement about the previous observations. Again, until you have photographs to show you're saying that you have made observations is just rhetoric. It doesn't do us any good.
I agree.
Okay.
I was simply presenting something. If I spent lots of time with lots more observations, we'd be taking even longer. But I'll happily provide these some other examples taken on different occasions. It's not a problem.
Okay,
and I'm quite more than happy. And if you do ever get to Scotland, I'm more than happy to go there with you if the weather's good enough. We can look at it ourselves and look at the other 8 observations made on the same hill of different things.
Can I ask you a question about this presentation right here? These 3 panes.
Yep.
Okay, so we have a building there, that white building.
Yep, that's a lighthouse.
Okay, a lighthouse. Fantastic, great. So if you go up to the top lighthouse and then just get an eyeball about the angular size, and then go down to the next lighthouse, it seems that the angular size hasn't changed, right?
Yep.
And then you go down to the next one, the third one at the bottom. Do you feel like you can see the lighthouse there?
Well, you can. It's not terribly clear. The beauty of that lighthouse is that the sad thing is I can't get quite far enough away from it for it to disappear altogether. But you can see it.
Right, right.
See
Yeah,
it
yeah. No,
night,
I get it.
light actually flashing, but it is there.
Yeah,
Yes,
I think
yes,
it's right
there
there
will be a
too. That's
small,
where
yes, there will be a small amount of compression,
that's where I
but
thought it would be too.
and
Sure.
going on, you're looking through what is obviously, a far more humid atmosphere directly above the water's surface than you are when you're looking down at, from a higher elevation. But the island on the right hand side here is gone completely. The next island along is only just poking up above the surface. And once again, you can argue that we have this ether band thing that causes this sort of effect, but the effect that your ether band causes exactly matches what we
Okay.
would expect to observe on a spherical Earth
The problem
of
is,
the
and
appropriate size.
yeah,
And so your job is not just to make observations which show refraction and things changing from day to day, especially when you take low angle pictures across the surface of water.
I need to
You
ask a question.
have to actually explain how and why it perfectly matches
Right. Yeah. And
those
I'm
observations. And I have the same islands
don't listen,
taken
don't change.
where
Don't
there is
change. Go
some
back. Go back,
refraction
please.
going on,
Miles,
where
don't.
there is some refraction going on, and you can see. But on this particular day, there was very
Okay.
little.
All right. So, let me say this. I am up to the challenge, and I have created a meme and a saying where I say I'm your Copernicus. Okay, so I'm up to the challenge. My question here about this observation is: Are these your images?
Yes.
Okay, and are these on the same day?
Um, the bottom two are taken on the same day.
Okay.
The top one is taken from a very, very slightly higher location on the cliff. Uh, it's the same observation. It was different. It was the same day, but different time of day,
Understood.
and it's a little bit clearer.
Yep.
It shows the outlines a little bit clearer.
Yep.
And that's why it's
Yep.
included.
Yeah. No problem. I'm just getting my bearings. So your mouse right now is on that third from the left.
Uh, over which
Well,
one? This one?
yes, that one. Correct. Right. So do you feel like you can identify that in the bottom frame?
Yeah, it's here. You can see that they're not perfectly lined up. The left-hand edge of the Bass Rock here is obviously not in line with the left-hand edge of the image above. So that's
Okay. So again,
and you expect the other one to be a little bit further over here. But
okay. So my immediate observation is that there is a very, very huge discrepancy between the distance between the lighthouse island and that little nub island.
yeah, and that's because this bit, okay, here is there.
Uh-huh. So again,
So this gives you this lovely reference that tells you just how much of that is actually missing below the horizon.
okay, I understand what you're saying. The difficulty that I have is that let's say, for instance, the bottom image, I do not believe that you can prove by angular size that that is exactly what's missing according to your math. I don't believe it.
I can take the I haven't got that here, but I can take the known elevations of those islands above sea level. What I would also need to do would be to account for the tide height, which I haven't done that on this particular observation. I went from this being my favorite place to go to deciding that observations over water, as it's shown in the next picture, where you can see that we have some clear inferior miraging going on at the surface. My preference was to try and take that out of the equation by not observing over water and going to an elevation above sea level and trying to find objects that I could line up in my picture. And I was lucky enough to find the Traprain Law and the Hopetoun Monument and the Queensferry Crossing bridges, all of which give me that 210 meter elevation.
Right. So let's take this image just real quick and say that you're going to apply the curve calculator, Walter Bislin, whoever you want, whatever the one you're comfortable with. The third island from the left, you are going to assert that whatever math you calculate from at this distance and height and all of that represents exactly what you see right here.
It will within the expected error limits of different refraction conditions, and that was the reason for changing my location. Was that what happens when you're talking about these sorts of observations? The same thing happened. I don't know if you were around when the dreaded Isle of Man observations were going on with Anthony
That's right
Riley
when I
Mason.
began. That's right when I began my flat Earth journey, and you were introduced to me as Miles the Liar, Davis.
If you can't attack the argument, attack the person. Yeah. So the argument is always with these kinds of observations, and I've only seen a few of your videos, but it's always a few feet here and a few feet there, at the most a few tens of feet. And the beauty of going up the hill and taking the pictures of the mountains in the distance, the same thing applies to the Mount Rainier, Mount St. Helens pictures that others have looked at, is that we're now talking about hundreds of meters and thousands of feet of missing or drop being demonstrated, rather than a few feet here and a few feet there where a bit of refraction or not can account for that.
So the one thing that I will try to suggest don't move your mouse crazy. I want you to stay on that island.
I can't see my mouse at the moment, so.
Oh, okay.
I've zoomed in somehow there. I didn't mean to do that.
That's okay.
That's another picture. Sorry.
That's okay. So you've got your mouse right there. Stay right there. So you see that little nodule to the left?
Yep. The bit of.
Correct. That is where I would. That is where
you see the sky reflect. Well, not reflected, but it
it's
appears
reflected. It's reflected
because of refraction.
It's reflected. I would put, if you could, a horizontal line right there and say that is where the inferior mirage begins, and then everything below it is blocking the physical island that is there, so that there is no absence of any physical part of the island, so that obstruction is never physical. It is never due to curvature. It is always, only, and ever will be due to the effects of the ether band.
And the fact that if you go far enough up the coast, you can make all four of those.
That's right. You're changing your angle. That's right. You're changing your angle, and you're going to totally change. It's It's just like if you were to say.
There's always a kind of excuse.
No, it's not an excuse, Miles. It's not an excuse, Miles.
The reason that I included these.
That's physics. That's physics, Miles.
Explain why the observations over water of this nature are not going to lead you to any understanding of truth or any understanding of what the reality really is, because of these refraction effects that are always going to interfere a few feet here and a few feet there. The suggestion that the amount of the Bass Rock, the left-hand island here, that we could have this much of the Bass Rock is somehow hidden in an ether band. I mean, how thick is your ether band here? You know, how can something that high disappear into something that's a few pixels high?
Sure.
It's
not. I
so
have.
difficult to imagine that,
I know.
and you, if you want that suggestion to be taken as a serious alternative to a spherical Earth, you have to come up with a really good mechanism, as well as an astounding number of observations, all of which show things always disappearing into that ether band. And the problem you've got is things like this, where you're seeing thousands of feet appearing lower than they should do.
That's right.
You know, it's probably 1,000 meters. It's probably about 3,000 feet. I think when I worked out the calculations, it was like 2,800 or 2,900 feet of drop that should be occurring there, and it's exactly what we observe.
So, as we wrap up,
Yeah.
I have my screen shared. Can you see my screen?
I'm gonna come out of this and get back to hopefully into yep. So I can see you now.
Okay. So what we have here is what I call my Monet shot.
Yeah,
Because it's
see
very
why.
reminiscent to me of
Yep.
Monet. I absolutely love coming out and finding these images. Okay, so what we have here is 3 different observations of the same location, and if you just keep this in your mind here, that we have this image, and we have no clarity in terms of shoreline here. Okay. So I'm going to open this one up and show you now that we have a bit more definition here of shoreline. This is all taken from the same location, same distance. It's just a different day, different conditions. And then this one here, which is about as good as I've ever gotten. And we've got even more. Now, again, this is proximate, okay? So it's not, you know, it's and the height is not thousands of feet, and the distance is not hundreds of kilometers.
Yep.
But the principle stays the same, and that is that the ether band is hiding the shoreline here and hiding the shoreline here.
No, you have. It's not. There's probably. I'm not even convinced that there's much in the way of refraction going on there. There's a bit, and there's a bit of distortion going on, probably the temperature. But you've got one where you've zoomed in and one where you haven't. So how
Well,
much
no, okay, so okay, hold on.
Yeah.
The only image that I would take issue with is my background right here, because I can look up the file, I'm sure. But both of these images,
building is still perfectly visible in the background. You can still see the.
That's not the point that I'm making.
Vegetation, and there's still and there is a sort of darker band just below that vegetation. Yeah, there's a bit of apparent reflection going on. So there's a bit of refraction going on there, but so what? Refraction of that sort of inferior miraging is a well-known observation. Has a
don't misunderstand me, Miles.
Acceptable explanation
Miles.
In terms of normal optics. If
Miles.
You want to claim it's doing something else, you've got to come up with your own explanation that really explains it.
Miles, please don't misunderstand my claim. My claim is that the obstruction is the effects of the ether band. Okay, so in again, I'm just going to do this for contrast. Here, we have no visibility of the shoreline. The shoreline is here. The water goes straight to the shoreline. If this ether band were not here, if it were clear, like it is right here, same
Yes,
location.
I
We
know what
have
you're saying, but
the
there's an alternative explanation which is called inferior mirage
no, that is the explanation. That's
refraction, and it makes a perfectly good
okay. Okay,
explanation for that.
right. Okay, Miles. So I based on what you just said, we are saying the same thing. The reason why you cannot see the shoreline here is because of the inferior mirage.
Yes.
Yes, that's what is happening at hundreds of kilometers and thousands of feet of mountains. It's the same thing.
Well, it isn't because or it doesn't appear to be because firstly it always appears the same, okay, from that location. Secondly, you can see clearly here where there are bushes being apparently reflected and inverted about that miraging line, if you like. Okay, and you don't see that in my observation. There's a very good reason for that. You don't see it because I've got myself up to a decent elevation. I'm not taking a low, very acute angle shot, and I'm not doing it over water.
All right, so you made the claim that you will have the same image each time. This is clear demonstration that you cannot and will not.
In that particular location where you're looking over water, different days with different amounts of humidity, different temperatures, and so on. Yes, it's going to look different. I showed you the pictures of
One picture.
those islands
One
in the
picture.
estuary, and they look somewhat different every single time you go because
Every single time. You only showed two pictures, Miles.
sorry.
You only showed two pictures. You haven't shown numerous examples of these um, uh, observations.
Which ones?
I'm just going to go back to the one with the lighthouse, right? The one with the lighthouse, you had three panes, okay? I mean, those are three different images, sure. Two of them were taken on the
Okay,
same day.
those islands are those islands. I've been to that particular little cliff top and that particular beach on many occasions, and they often eh, look. I mean, it looks broadly speaking the same, but you'll get some days where there'll be more or less refraction. Okay, and that's because you're looking out over water, and we know that that kind of refraction effect where you get temperature inversions of the atmosphere near to the surface of the water happens a lot, and you get different amounts of humidity depending on how hot cold the water is and how hot and cold the air is. That sort of thing is known and is understood, and there's a good explanation for it. Those kinds of observations, like the one you've got on screen, have a good scientific explanation that matches or that explains what we actually observe in reality. The same, well, not the same. The observations that we make over longer distances, for example, the mountains that I showed, and from higher elevations, if you look out over water to where an island should be, if it's too far away, you can't see it, or you can see half of it. I mean, the Isle of Man, those guys in the end had to accept that what they were looking at was the Isle of Man, and that they couldn't see all of it. And the only reason they couldn't see all of it was because of the well, they didn't accept it was curvature, but that's the only explanation that makes any real sense.
That's incorrect.
The way that observations change over time. You get a bit of miraging effect, and you see a bit less. But when there's no miraging effect there, and Alkay and I produce some really nice pictures where there appears to be no inferior miraging effect occurring, and you still don't see down to the shoreline. You don't see anything like down to the shoreline.
That's because the accuracy of your eye to see at that angle is also under the influence of the ether band at that distance and
Which
angle.
is why you go up to a couple of hundred feet above sea level,
That
a couple of
completely
meters, above sea
changes.
level,
The
take
fact
an
that you
observation over a longer distance of a big thing like
The,
a mountain.
the fact that you don't understand that when you change your height, it's just like changing your distance. You're going to change the observation.
Demonstrate that.
It's in
Demonstrate.
every.
Actually demonstrate that that happens. Okay, if you can demonstrate that that these sorts of observations actually have an alternative explanation, then I'm all ears. But to date, all that you or anybody else has done is said, "Oh, but that's going to happen because of atmosphere." Well, how? Explain it. Don't just say it's going to happen.
Understood. And if I had the ability, I would have the ability to lower my observation. I don't have the ability outside of maybe 5 feet, but then I would have to change my location, right? So from where I'm at, the only thing I could do is drop down to the shoreline to make these observations. So that would be changing, but that would be a 5 foot elevation difference. The last thing right here that I want to show you again, this is the same image, or I'm sorry, the same observation, same location, same viewer height, same focal length, but we have again a different representation here of what is in front of us.
And you know, the physics of refraction and optics explains why you see that on different occasions. Okay, and if you want to be taken seriously, you're going to have to come up with an explanation that is just as good.
I'm not trying to.
You seem to be completely in denial about all the observations that match the spherical Earth. We barely scratched the surface today. You've seen a few of mine, and I showed you some pictures of Earth from space. There are literally thousands and thousands and thousands of observations and different ways of working out what shape the Earth is, all of which fit with the Earth being a sphere, and none of which fit with the Earth being flat.
Okay, so let me try to pinpoint my position, because I agree with you, Miles. I 100% agree with you with your scientific reliance upon the dynamics of refraction. Okay, that's not where my argument is, and you and I are on the same page with that. When we see the end of the water line that becomes the horizon, as far as I understand the globe model, that becomes curvature.
No.
No?
Well, no. The curvature exists right from.
No. Don't. No, I'm talking about the horizon line, Miles. The horizon line. When we see the end of
line is an imaginary thing.
You seem to be wanting to hold on to a concrete horizontal line in one of your images.
Appears to meet the sky. When you look out over water and there's nothing in the way. Where the water and the sky appear to meet is your horizon line. Now that is if given your observer height, that is a particular distance away from you.
Right. This island is
going on all the way to that horizon line and on beyond it.
Okay, this island is 3 miles away from me, and I'm at 5.5 feet. So the curvature is here because at 3 miles there's 6 feet of drop. Okay. My point here, Miles, is this. This is my argument. This inferior mirage that we're looking at right here is blocking the water that continues to extend to the shoreline. And this image over here shows you the water extending to the shoreline. This image right here doesn't show you the water extending to the shoreline because it's behind an obstruction.
No, it's not behind an obstruction.
Yes, it is.
No, it isn't. There is no obstruction.
Where's the shoreline?
Is the light from the distant object, the building on the shore and the vegetation on the shore on the opposite side is being distorted so that you actually see it twice in two separate places.
Where do you see?
Not being obstructed. If you had a flashlight, or a powerful enough flashlight or a laser or something on that shore, and somebody switched it on, it would be visible.
I have observations of that, not here,
Yeah,
but
yeah,
from a
but
different location.
it would be visible, wouldn't it?
That's correct. That's because it's
Yeah,
directly in front of me. It's not behind a curve.
correct. It's not behind a curve.
Okay. All right.
Okay. Now, if you're going to argue that the calculators say there should be some portion of this hidden behind the curve, okay, go and measure it on multiple occasions and show that it
I don't
never
have to do the math.
ever
I don't have
goes
to do the
below.
math. I don't have to do the math on multiplications. The math doesn't change, Miles.
No, you have to do the observation on multiple occasions, not the
Right.
math, the observation,
Yeah,
and
I
you
have
have to show that
hundreds and thousands.
it never goes below the curve, and then you have to say, well, is there always going to be some of the opposite kind of refraction? Because you get looming sometimes, you'll get interior mirages.
Looming is simply magnification.
Sorry?
Looming is simply magnification.
Pretty much, yeah, but it still has the effect of allowing you to see things that by pure geometric maths should perhaps not be visible. Because the light is bent, you end up with objects being effectively, or in your field of view, lifted up above what is an apparent horizon. My point to you earlier was that all you will end up doing is arguing about a few feet here and there, and until you can show something that involves thousands of feet, as I have done,
I don't need to do that.
You've got no justification for your
That's
claim.
incorrect. That's incorrect. I don't need to have a scale of thousands of feet if I can demonstrate it on a smaller scale. So one of the things that I wasn't able to demonstrate to you, and if you're willing to come back, then you had a great presentation, right? And we talked about that a lot.
Yep.
I can present to you different footage of the Anacapa Island, which is 20 miles away. And I have such divergent observations that I think it would be a very interesting discussion for us to have.
I'd be quite happy to see those, but and maybe I'll be proved wrong, but I very much doubt that we're going to see that you're ever going to see anything that is not easily explained in terms of refraction.
Again, I don't disagree with refraction affecting the observation. My claim is that when we look over vast distances, the reason why we interpret the obstruction from the bottom up as curvature is because we don't understand that it's actually refraction that is blocking our ability to continue to see that object according to perspective.
Which is why I went to something where there is no bottom up loss of observation. By going to where I went, I could show that those objects are there, but are below where they should be in our field of view if the Earth is flat.
And my outstanding request would be that you provide numerous observations from that location.
It's not the easiest observation
you
to
are
make.
absolutely correct.
Distance array and involves climbing some hills, so it's not the easiest thing to do. But
I will not argue. I will not argue with you on that point.
Right, I have to go. I have a client waiting.
Yep.
Fairly soon. So
Miles, honestly, Miles, thank you so much for giving me your time.
Yep,
and let's keep in touch and let's try to set another follow-up appointment.
That's okay. Yep.
Great. Thanks,
Okie
Miles.
dokie.
Okay.
All right.
Thanks.
Cheerio.
Cheerio. Pip, pip. Okay, everybody out there in the Plain Truth land, how you doing? I can now look at the chat. It is 11 o'clock. I cannot open up the chat to bring in this. I would love to do some follow-up. Oh, Workhorse, can I join the chat? If I do that right now, I will not get ready for work. I am so sorry. You know, maybe we can do a follow-up tomorrow. Tomorrow's Wednesday. I don't think I have any scheduled appointments. Let's do possibly a hangout tomorrow. I'll open it up. Allie B, always welcome. We can do a discussion here if you've listened to this entire presentation. Yeah, so thanks for being here, everybody. I appreciate that. Derek O'Hara, Workhorse, Flat Earth Bear, Allie B, Ron Hagberg, and Danielle, Eyes to See When She Was Here. All that kind of good stuff. So I guess that's it. That's about it, guys. Thanks so much for being here. And yeah, this has been The Plain Truth from Our Perspective, episode 9. I'm your host, Travis Finley.